Okay, we've talked about solutions before. We've been talking about them all semester, really. So there's really just a few things that we're going to be more particular about in this chapter that are a little different from what we've done before. So first, let's just remember that solutions are really just a type of homogeneous mixture. Homogeneous mixture is a little bit more general of a term. Solution kind of assumes that those things are integrated at the smallest possible level. And we'll look at that throughout this chapter. But in a solution, the individual molecules of two different parts two or more different things are coming together and really interacting in a particular way. So we're going to define two terms, the solute and the solvent. Have you heard these terms before? Yeah, so which one is which? Or what are they? The what? The solvent is water, usually. Like what you dissolve in it? Yeah. Yeah. So we think of solutions as usually like one thing. And we're gonna see they're actually pretty different, but the main one we always think about is something like salt and water. You take some salt, you dissolve it in water. In that case, the salt is the solute and the water is the solvent. The solvent is the thing that you dissolve it in. But solutions are actually more general than that. So we can't just say the solvent is the liquid or the solvent is the water, because that's not always the case. So we're going to say the solute is what there is less of, and the solvent is what there is more of. And that's really as specific as we can get. The only difference there, I'll make a little note here, when there's water involved, and there's not always water involved, but when there is water involved, water is almost always the solvent, even when there's less of it. We'll see some examples of that. All right, so the first thing to remember about solutions that you may not think about when we have that typical like saltwater example is that solutions can be in any state. They can be liquids and gases and solids. And there's a nice table in your book that I'm going to pull for this. This is page 283 if you're following along. We're going to look at some different examples of solutions of different types. So take a look at this table. First of all, it's split into three different types: gas solutions, liquid solutions, and solid solutions. So there's not just that standard one. The one that we're thinking of with the salt and water is right here. Whoops. Is right here. But that's only one of a whole bunch of different possible types of solutions. So you can have, for instance, a gas dissolved in a gas, like air. Air is a solution. And we might describe the nitrogen as being the solvent because that's what most of air is, and the other gases being solutes. Oxygen would be one, carbon dioxide, water. The other types of gases in the air are the solutes. In liquid solutions, you can dissolve gases, liquids, and solids in liquids. So the solid and the liquid we've talked about, like salt, water, dissolving sugar in water, that kind of stuff. But you can dissolve gas in a liquid. You can dissolve carbon dioxide in a liquid. Oxygen is dissolved, like fish, right? Fish couldn't breathe. Fish couldn't survive if they couldn't get oxygen out of the water. That's because the oxygen is dissolved in the water. So that's a solution of oxygen in the water. You can also have liquid in a liquid. So we had our 5% vinegar solution the other day when we were looking at the conductivities. That would be acetic acid dissolved in water. You can have, this is where it can get a little weird sometimes. because two liquids, you know, you can change, depending on the liquid, you can change their amounts pretty much the whole way. So if you take something like ethanol and water, ethanol is like drinking alcohol, right? You can have very low concentration of alcohol, you can have higher and higher. I don't know if you've seen, you can get almost pure alcohol. It's like 95%, they call it. And that's really kind of a weird thing, because if it's 95% alcohol, isn't it then a solution of water and alcohol instead of alcohol and water? So that's why we said when there's water, water is usually still the solvent, even though the other one there might be more of. And then you also have a solid solution where there's a solid and a solid. And this is kind of, we looked at some of these examples with homogeneous mixtures. We called them homogeneous mixtures, but they're also solutions. So they're really also one thing dissolved in a matrix or in a bunch of something else. So you can call brass a solution of zinc and copper. You can call steel a solution of carbon or chromium or some other things in iron. All right, so different types of solutions. Solutions don't have to be just a solid dissolved in a liquid. Let's think about how solutions form and what that means. And we're going to go back a couple chapters to when we talked about our intermolecular forces and how things are attracted to each other. And let's just stick with that salt water example, because that's the basic one that we always think about. So when we make a solution, we're going to take solid sodium chloride. We're going to dissolve it in water, in liquid water. Now, when we write those two things, let's think about what that means, what those two things look like at the molecular level. So what does sodium chloride look like at the molecular or atomic level? How do you describe it? That's at the bulk level, like that's what it looks like. What if you could see all the way down to the individual atoms? How would they be arranged? What would it be like in there? What is it? How is it put together? Ideas? What? Not quite. Remember that sodium is a metal and chloride is a non-metal. So inside there's going to be ionic interactions. So there's actually not sharing of electrons like those bonds. So that's what we can draw, that there's ionic interactions between positive sodium ions and negative chloride anions. And that might look like this. We might have, let's say, a sodium ion, and then a chloride ion, another sodium ion, and so on. Right, the negatives attracted to positive, positives attracted to negative, so those are going to pack in as tightly as they can so that the negatives and positives can be as close together as possible. So it's this tightly packed structure of little spheres being held together by those electrostatic forces, those positive and negative forces attracting each other. All right, what does water look like on the molecular level? How is it different from this? Yeah, so an individual molecule of water is going to look kind of like this. And then what's going on around it? More of the same thing. Right, more of the same thing, right? And they're anybody remember what it's called? The thing that connects different water molecules together? The hydrogen bond, yeah. So we're going to have different water molecules connected by hydrogen bonds, these intermolecular forces that go from the positive side of the water molecule, which is the hydrogen, to the negative side of another one, which is the oxygen. And they end up making this whole big network. You can keep drawing these around. They actually make a really well, in the water structure, there's less order. When they crystallize into ice, they make this hexagonal structure. But in water, they're all kind of close together, interacting like this, connected together through these intermolecular forces. We could draw these kinds of things to show that attraction. Remember, we did that before. So that's all water molecules. All right, so we got these two things that are pretty happy individually. You've got sodium chloride, which has these strong positive and negative attractions. On the one side, you've got water, which has its own intermolecular forces held together pretty strongly on the other side. So why do these things form a solution? Why do they mix? Why don't they just keep together? So let's take a look at that. If we're going to put them together in a solution, what that means is we have to break apart those interactions. And that wouldn't happen unless there were new interactions forming that were just as good or better than the old ones, energetically speaking. So what happens is the individual ions, like in the sodium chloride structure, break off. And they become what's called hydrated, which means water is added to them, and water molecules end up surrounding them. So we've got, remember, negative side of the water molecule is the oxygen side, and the positive side is the hydrogen side because of the electronegativity. So what will happen is the water molecules will surround the sodium ion, kind of pointing the oxygen partially negative part at the sodium ion. Right, those partial negatives are attracted to the positive. And we draw it kind of as like that, but in reality it would be a sphere. So all the way around the ion would be these water molecules surrounding it. And then the same thing is happening with the chloride, just with the opposite side of the water molecules. So here's our negatively charged chloride ion with hydrogens pointed at it. Right, that kind of thing. And then because there's so much more water than there is sodium or chloride, these things end up kind of making, we might call bridges between them, so that that hydrogen bonding network stays intact. Getting to the bottom here. So that water network of all the water molecules attracting each other is still there, but they've now fit the sodium and chloride ions into them and made this nice sphere that surrounds them. And the net effect of all of those interactions is that that's actually more energetically favorable than those things being by themselves, than the two parts being by themselves. So this is how a solution is formed. This is the molecular view of a solution. The ions themselves are broken apart and then surrounded by the solute, or by the solvent molecules. And that's true for any solution.
Can you repeat that?
Yeah, the solute molecule, or the solute particles, whether they're ions or molecules or whatever, are separated from each other, from their own intermolecular forces, and instead mixed with the solvent molecules. And the solvent molecules surround and encapsulate them. All right, so let's look at how this works now with some things that aren't soluble, like water and oil, or a polar and a nonpolar thing. We talked about this back in that chapter when we were talking about intermolecular forces, how the different types of forces don't mix that well. And when we think about why they don't mix that well, we can think about it in these terms. So if we said something like oil, which is a bunch of carbons and hydrogens in a long chain, so we're just gonna approximate it by drawing this big zigzag, because that's kind of what it looks like. Okay. We're going to call that oil. Just think of a bunch of carbon atoms connected with hydrogen surrounding it. And those interactions, do you remember what those are called? How do those things connect? Starts with a D. Well, that's the polar one. What's the one for the nonpolar molecules? Now, the right beginning. All right, it's dispersion forces. Dispersion forces. They're those nonpolar forces, those induced dipole forces where they just kind of momentarily have that offset of electrons, then they end up all lining up. All right, so you got these oil molecules hooked together with dispersion forces. If we have that same kind of water network that we had before, with water molecules held together with hydrogen bonds, however we want to draw that. Now we have two different types of intermolecular forces. So there's nothing favorable, there's no stabilizing energies of these things connecting. Because if they connect, they have to do the same thing that we did before with the sodium chloride. The solute, in this case the oil, has to break its dispersion forces apart, and then become surrounded by the water molecules. That's not going to happen because the water molecules would then have to break some of their interactions. And when the water molecules are surrounding the oil molecules, there's no good intermolecular forces there. Because you've got a polar molecule and a nonpolar molecule. They don't have the same types of forces, so they're not going to interact well at all. So that's why things that are insoluble, things that don't dissolve in one another, it's because of the forces. They'd rather stay together. They'd rather stay with their own types of forces and not mix with the opposite, because there's no stabilizing force in mixing with the opposite one. So in general, we can think about this idea of polar and nonpolar, where polar solvents dissolve polar solutes and nonpolar solvents dissolve nonpolar solutes. That's not totally right, because it's really about the intermolecular forces. And you can have a nonpolar molecule that still has some kind of polar forces in it, and vice versa. But in general, it works pretty well to think about the forces in the solute, think about the forces in the solvent, and see if they mix or not. Okay. Is there a thing about? All right. The other way we can describe a solution is in terms of its electrolytes or electrolytic capability. And we talked about this in lab back when we were looking at ionic versus covalent solutes or structures. Do you remember the thing with the light bulb? We put the solvent in the light bulb and it either lit up or it didn't. And that's because the solution was either an electrolyte or it wasn't. So we're going to define these things. We're going to define a strong electrolyte as something that dissociates, so breaks apart. That's what dissociates means, like the opposite of associate. So it breaks apart and produces ions in solution, so charged particles in solution. And mostly, strong electrolytes are going to dissociate completely. So almost 100% of the formula units split up and form ions. So those can be ionic compounds like sodium chloride. They can also be acids like HCl. We tested some of those. Some acids will also dissociate and form ions in solution, and those are also known as strong electrolytes. This language is going to be important in the next chapter also when we talk about acids and bases, because the opposite here is a weak electrolyte. And a weak electrolyte is something that mostly stays as neutral molecules in solution. So that would be like the acetic acid in water that just made the light dim a little bit, or turn on a little bit, but very dimly. And then we could even put a third category on there. I don't think the book does. Oh yeah, okay, it does, sure. So we'll say this is some ions formed. The last one is going to be the non-electrolyte. Which is going to have no dissociation in solution, no ions formed. So for examples, something like NaCl is a strong electrolyte. Also, strong acids like HCl dissociate, produce lots of ions in solution. A weak electrolyte mostly stays together, produces a little bit of ions. So something like acetic acid, vinegar. There was also one of the antacids, like the milk of magnesia, which just let the light out up a little bit, and that is because a lot of that is staying together, some of it is breaking apart. And then the non-electrolyte are the molecular compounds that don't dissociate, don't produce any ions at all. So things like sugar. Sugar still dissolves in water, but it doesn't break apart when it dissolves. It stays as a whole molecule. The other water molecules just surround it. This language becomes important in the next chapter with acids and bases. As we'll talk about, we separate acids and bases into categories of strong acids and weak acids, strong bases and weak acids, or and weak bases. And we think about those categories as meaning like how dangerous the acids are, like strong acids burn you and weak acids don't. That's not really true. It just has to do with how much of an electrolyte they are. And so a strong acid is one that breaks apart and forms ions, and a weak acid is one that really doesn't. So that's where this language mostly comes from. If you want to see kind of why that works, or why the conductivity works, it's because the charged particles allow that electric current to flow through the solution. So the electrons can move through as the positive or negative ions can also move in the solution. And so that's why strong electrolytes allow electric currents to pass and weak electrolytes don't. If you've taken, has anybody taken physiology? They kind of go through some of this stuff too, right? Like how that works in the body. It's important to have, is it sodium and calcium? And those are making the nerves do stuff. I don't really know how it works. Okay, yeah. So you need ions in solution to be able to carry that electric current, right? Oh, it's in the book right here. Yeah, I should read it. Then I'll know. Okay. We measure this, and this is one thing we'll do in lab on Wednesday, this idea of can you make a solution or not like this? We can measure how much of the salt you can actually get in the solution. Because what happens if you, let's say you're making a solution, you're making salt water. You're dumping salt in the water, you're stirring it up, it's dissolving. You keep dumping salt in, what happens eventually? It stops dissolving. Does anybody ever have that experience? Or like with sugar, you keep putting sugar in, but it's still not sweet enough to keep putting sugar in, and then eventually there's just a pile of sugar on the bottom, and then you feel bad about yourself because you feel like you should probably just grow up and drink your drink without so much sugar, but just sharing personal experience here. But yeah, eventually you put enough solute in, it doesn't go in anymore, it just drops to the bottom. So why is that? How can we use these kinds of ideas to explain what's going on there? Why is there a point at which the solute won't dissolve anymore?
There's no more like
Solvent, right? Is that what you're gonna say? Also, she was saying like eventually there's just not enough solvent to kind of put it together, right?
Yeah, that's what I was kind of trying to say.
Yeah, and that's pretty much right. So for every substance is going to be different, but based on how strongly the ions or the pieces of the solvent attract each other, based on how compared to how strongly they attract the solvent, at some point this solvating spheres, these spheres of solvent molecules that are surrounding the solute, are just not strong enough to prevent them from coming in contact with each other. Remember that sodium and chloride are fully charged ions. They're going to attract each other very strongly. So in order to keep them separate, there needs to have plenty of water. There needs to be plenty of water around them to keep them in these spheres and unable to connect. At some point, there's not going to be enough water around anymore to stop them from joining back up again. And so they join back up again. So that whole kind of dynamic is what we refer to as the solubility. How much of a amount of solute can you actually get into the solution? So let's say you have 100 milliliters, or it's usually done by mass, so 100 grams of water. How much salt can you add until it stops dissolving? That number, whatever that is called the solubility. So if you can put 35 grams in before it starts just falling to the bottom without dissolving, that's called, then you'd say the solubility of that solute is 35 grams per 100 grams of water. Does anybody know what it's called when you've put all of the stuff in that you can? There's a word for it, for the type of solution that has all of the solute that it could possibly hold. It's a saturated solution, yeah. A saturated solution contains all the solute that can possibly dissolve. So that's the most you can get in there. This is kind of interesting also. How do you make a saturated solution? So let's say you want to make sure that your solution is perfectly saturated. Any idea how you would do that?
Filter out the excess stuff that didn't dissolve.
It's actually, yeah, it's even easier than that though. What you do, because if you filter, so what you're saying is you like dump a bunch in until you're past the point where it's all like sitting on the bottom, and then you would filter off the excess, right? That's good. The problem with that is, let's say that it absorbs some water from the air, which it's going to do, because now that it's saturated. So once it absorbs some water from the air, it's no longer saturated. So there's this constant back and forth going on. So the better way to do it is actually to leave all the junk in the bottom. Because now, if it absorbs more water from the air, it can also then dissolve more from the whole stock of stuff that's sitting on the bottom. So whenever you have a saturated solution, like on Wednesday we're going to use a saturated solution in lab, it's going to have a bunch of stuff stuck to the bottom. Like it's going to have a pile of solute still sitting on the bottom. Because in order to make sure that that solution is always saturated, you need to have a source of solute in case it needs a little bit more. And then just from this back and forth that we call equilibrium, it'll balance itself out and it'll keep itself saturated. And then what you do is you just pour carefully so all the stuff stays on the bottom and doesn't get into whatever you want to get into. And then you have a saturated solution. There's a picture of this in the book on page 291. So in your unsaturated solution here, you'd have, whoops, how did I do that? In your unsaturated solution, you just have some stuff dissolved in the water. In the saturated solution, you always have stuff on the bottom, and there's this constant back and forth of dissolving and then recrystallizing to keep that perfect balance in there. That just happens automatically. So the next question is solubility fixed? Like, let's take sugar, for instance. Anybody else like very sweet beverages? I don't know, I'm the only one. Yeah. So if you put a bunch of sugar in your beverage, does it matter if it's hot or cold? How?
The heat will make the solvent.
Well, you don't have to use fancy chemistry words, but like,
The heat
what
will make
happens?
The sugar melts into the solution to make it warm.
Yeah, has anybody else experienced that? It's a lot easier to add sugar to a hot beverage than a cold beverage. Like if you try to sweeten iced tea, it's just frustrating. It just falls to the bottom. Okay. Yeah, so solubility is temperature dependent. Solubility is not always the same. Solubility depends on temperature.
That also work with like solid and solid. Like that's solid.
Kind of. It's a little different because you can't make the solution when they're both solids. So they have to be molten to actually make the solution, or one of them has to be at least. So that kind of complicates it because now it's not really a solid solution anymore, and then when you cool it back down, it is again. So yeah, it's a good question. I don't think you can say that exactly the same way like that, because it has to be melted to make the solution in the first place. So if we look at this, which doesn't, this is what we call a solubility pot. And we're actually going to make one of these experimentally on Wednesday. But what this shows, I know I cut off the bottom, but the bottom is temperature. It shows how the solubility changes in temperature. So as the temperature increases, the solubilities go up. And I should say, that's not true of every solute. Some solutes actually lose their solubility as the temperature increases, but most solid solutes, the solubility goes up. The amount it goes up changes greatly. So like glucose, which is a type of sugar, you can see you heat it up a little bit, and you have a huge increase in how much you can dissolve. But salt, sodium chloride, the solubility barely changes. So it's really not that much easier to dissolve salt in hot water than in cold water. It's about the same. So for most solid solutes, solubility increases with increasing temperature. Not for all of them, but for most of them. So there's various reasons for that depending on the solutes, but a lot of it has to do with having enough energy available to break apart the solute interactions inside the solute. That you can, when it's at higher temperature, you have more energy available to break those things apart. You also can break up the interactions in your solvent matrix more easily, so it allows the solvation spheres to form more easily as everything's moving around more. The opposite is true with gases. With gases, the solubility goes down with temperature. So for instance, carbon dioxide, if you've had carbonated beverages, if you have an open carbonated beverage, you leave it out on the table, it goes flat, right? You put it in the fridge, it still goes flat eventually, but it takes a lot longer. So the colder temperatures allow the carbon dioxide to stay dissolved more easily. And that's known as Henry's law. But they use that same example actually in the book too with the soda, that at higher temperature, more gas is being produced. Or if you ever notice, like, if you have a drink that's in the refrigerator, like a carbonated drink that's relatively full, and you take it out, you let it warm up to room temperature, or you put it in a hot car or something, it gets really like it's gonna explode. And that's because of all that extra gas coming out of it, because the gas is no longer soluble enough, and so it is coming out the top of the solution and becoming higher pressure inside there. Oh, okay, there we go. So what we're going to do on Wednesday, we're going to take this potassium nitrate, which is KNO3, and test its solubility at a variety of temperatures. Different groups will do different ones. And by putting all the class data together, we should be able to construct a solubility curve that looks like this, that has the different solubilities at different temperatures. And so we'll work on that on Wednesday. There's kind of a neat technique that you use to try to find that exact spot. Okay, so that's all the kind of general stuff with solutions, general ideas. Let's get into some more specifics, and that is what we call concentration. We've used this word before because of stuff we've been talking about in lab and so on. But now we want to really define what we mean by that and how we calculate it for different types of solutions. And this is something that is definitely important as you go on in medical fields. Any kind of medications or anything that involves being dissolved in something usually is going to have a concentration associated with it. Remember how when we talked about gases, we said mass, volume, it's not really a good way to measure it, so we use pressure because that was a more direct way of measuring how much gas we have. Well, with solutions, it's kind of the same thing, but now we need this thing called concentration. If you have 100 grams of a sodium chloride solution in water, that's not really a helpful thing because you don't know how much of that is sodium chloride, you don't know how much of it is water. It could be a little bit of salt dissolved in water. It could be a whole bunch of salt dissolved in water. So we need this information, the concentration, which tells us how much solute is dissolved. In general, we can define concentration as the amount of solute, whatever it is, divided by the amount of the solution. So that's concentration. How much solute is there in a certain amount of solution? Now, the actual units that we use for that vary greatly, which is why I just said amount here. So there's a whole bunch of different ways that we can define amount, what we mean by amount. And we're going to go through a couple of them, and the couple that we specifically use most often. So first, probably the easiest one is what we call mass percent. Mass percent is sometimes written percent m/m. And this is the value that you get when you say amount as mass. So the amount that we're dealing with is the mass. So that mass percent is going to be literally the percent of the overall mass that is due to the solute. So the mass of solute divided by the mass of the solution. And then technically we say times 100% because that division, there's always going to be less solute than overall solution. So that becomes a percentage. But hopefully you've dealt with percentages in the past, so that shouldn't cause too much trouble. The tricky thing here is that we have to make sure that we remember that the denominator here is the mass of the solution, the total mass. We always want to make it the mass of the solvent, and it's not. It's the mass of the solution. So for example, a problem like this, what is the mass percent of the solution prepared by dissolving 30 grams of sodium hydroxide in 120 grams of water. So we look at that formula. The formula says mass of solute divided by the mass of solution. Look back at the problem. What's the solute here? NaOH, yeah, the sodium hydroxide is the solute. So our mass percent is going to be the mass of the sodium hydroxide, so 30 grams sodium hydroxide. And then what's the mass of the solution? Yeah, careful. So 120 grams is the mass of the solvent. That's the mass of water. The mass of the solution is the whole thing. So it's going to be the 120 and the 30 added together. That's the whole mass of the solution. So you have to make sure to add the solvent and the solute to get the total mass of the solution. All right. So if we divide those, you get 0.2, which we would say is 20% if we multiply by 100%. So the way we would write that is 20% m over m. That m/m is important because there are various ways of measuring concentration. Mass percent of one is one of them, but there are other ones too. So there's V over V and there's m over V also. So we have to specify which one we're talking about. All right, that's about the halfway point. So let's stop and take a break there, and then we'll talk about the other units of concentration and do some practice with some of those calculations, including the most important one, which is molarity. Of course. All right. So we looked at mass percent. There's a couple others in the book, volume percent and mass by volume. Those are used, and you can look at them. We're not going to go through them now. They're not going to be on the quizzes and exams. Just don't want to get too confused, and we want to stick to the ones that are most important for our use. So that's going to be mass percent, and the next one we're going to look at, which is molarity. So if we go back up to our definition, amount of solute over amount of solution. Those amounts can be any kind of a unit that means amount. So it could be grams, it could be volume, like liters, milliliters, it could be moles. For gases, it could be something like pressure. So the first one, the mass percent we did was mass of solute, mass of solution. There's volume percent, which is volume, and there's mass by volume, which is mass divided by volume, so grams divided by milliliters. Those are all ways of measuring concentration. The one that we use mostly in chemistry, and we'll see why it's most useful, is called molarity. Molarity, as you can maybe guess from the name, has to do with the moles. So instead of doing grams, instead of looking at the mass, we look at the moles. And the formula for molarity is the moles of solute divided by liters of solution. So you can think of that as moles per liter. You can think of it as moles divided by liters. That's how we find molarity. The reason that's so useful in chemistry is because, well, with the stuff we did a couple chapters ago, where we always had to find moles to be able to figure out the ratios for the reactions. If you've got solutions, it's way easier if your solutions are already characterized in moles. And molarity is the way that we do that. So let's look at an example. Let's look at our, well, we can't exactly look at that. Let's look at a slightly different sodium hydroxide solution. So we might ask, what is the molarity of 60 grams of sodium hydroxide in 0.250 liters of solution? So to do this, we need to do the calculation above. Moles of solute divided by liters of solution. Well, liters of solution we're given, that's 0.250, so that goes on the bottom. But on the top, we need moles of solute, not grams of solute. So how do we do that? What do we do? If we're given 60 grams, how do we get that into moles? But, right, we're going to do a conversion. So we're going to go $60 grams, and we're going to multiply by a factor that gives us from grams, canceling grams, and gives us moles instead. So what kind of a number gives us the relationship between grams and moles? What's that called? For a given compound, how do we know how many grams are in moles? Yeah, the molar mass, right? So we know we need the molar mass of sodium hydroxide to be able to do this. So we're going to add that up. Sodium's 23, oxygen's 16, and hydrogen's 1. So that's 23 and 17, that's 40. 60 divided by 40 is 1.5, right? Is that right? Yeah. So we've got 1.5 moles of sodium hydroxide. Now we have moles of solute. We have liters of solution, so we can calculate the molarity, concentration. So if you divide those two, you get 6. And the way that we say this is we say that this solution, the concentration of the solution is 6 molar NaOH. We use a capital M for molarity. So we would say 6 molar, just like the tooth. All right, so we've got 6 molar, that's our concentration. So that tells us how much NaOH is in that given amount of solution. So that's an extra step to calculate if we're given a mass, but it saves us a step if we're then going to use that in a reaction, because we already have the moles. So we know, for instance, if we have a 6 molar solution, that every liter of solution gives us 6 moles of sodium hydroxide. So we can always easily figure out how many moles of solute we have in this kind of a calculation. All right. Let's look briefly at how this is done, because you're going to be doing this in lab. So the experimental way that you make a solution to a certain concentration. You use this type of glassware called a volumetric flask. It's got a long, skinny neck with just one line on it. And it only measures one volume, but it measures it very precisely. So you might use like if you wanted to, in the example we just did, 0.250 liters, that's 250 milliliters. So you use a 250 milliliter volumetric flask. You put your solid in there, and then you add water and mix it until that mark is reached. And that tells you have that way you know that your total solution volume is whatever the size of that glassware is. Because if we go back to the thing here, remember that we want liters of solution on the bottom, not liters of solvent. So you don't measure out 250 milliliters of water and then mix it, because the solute has volume too. So you need to add it together and then go fill it up to a particular amount to get the correct concentration of that solution. All right. So let's look at how we would use molarity in a problem where we're calculating some different things we may want. How much of a 2 molar sodium chloride solution contains 0.50 moles NaCl? So this is how we can use a concentration like that. We have a reaction, or you have a treatment or whatever, where you need half a mole of sodium chloride, 0.5 moles of sodium chloride. The solution that you have is 2 molar in concentration. So how much of it do you use to get to that 0.5 moles of sodium chloride? We treat this just like a conversion problem. So we treat this as a conversion problem where we're going from moles to liters, and we're going to use that concentration to tell us that relationship. So we can say 0.50 moles of sodium chloride. And then we're going to multiply that by a factor that cancels moles and gives us liters. The relationship between moles and liters is given by the concentration. Remember, the concentration is defined as moles per liter. So the fact that it's a 2 molar solution tells us that there are 2.00 moles in each liter. We get that from the concentration. All right, so we do that division, moles cancel, and we end up with 0.25 liters. So 0.25 liters, or 250 milliliters, of this 2 molar solution would contain 0.5 moles of NaCl. All right, let me copy a couple over from the book, and you can practice doing this. We won't do a whole bunch of them, but just to give you a sense of what these questions look like. And we'll go through a couple as well. All right, so for this one, let's just do B. And A. So see if you can figure out first what would be the molarity of 4 grams of potassium hydroxide and 2 liters of solution. And then how much solute would you need to make 2 liters of a 6 molar sodium hydroxide solution? Second one's a little trickier. We haven't looked at how to do that yet. So see if you can figure it out just by thinking about it like a conversion problem or like units. Oops. Sorry. All right, should we take a look at these together? Are you still working? I legitimately can't tell. Do you want? Are you still? It's like people are sort of writing, but not really. I don't know. Should we look at them? But you're good. Okay. Thank you for answering. So we'll do it. Okay. I'm just gonna move this out of the way so we can do this one. All right. So this first one is the same type of problem that we did earlier. So you need to convert the grams to moles and then divide by the volume of the solution. 4 grams of KOH, and when we want to go from grams of KOH to moles of KOH, we do that by looking at the periodic table and adding up the masses. So that's 39.1 plus 16 plus 1. So that's 56.1. Is that right? Yeah, okay. That's right. So 56.1 grams per mole. And what do you get if you divide those two? 0.071. Okay, so that's our moles of KOH. So then we have to divide it by the overall volume of the solution that we're making. So 0.71 moles of KOH divided by 2 liters of solution. Like 0.346. 0.03. Oh yeah, oh this would be 0.0. Yes, thank you. Okay. So 0.0. No. You said I did. I just copied it over wrong. So 0.355 molar. So we use a big M to make molar. I usually put like a little curly thing on the end. I don't know. That's not really necessary. If you look at the book, they do like they just use a capital M. Some books use like a scripty kind of capital M to make it look different. It doesn't matter. Capital M is fine. So that's our concentration. That's the molarity, 0.0355 molar. Yeah. 56 is fine. I just didn't round. So if you look at potassium, it's 39.0983. So you could have picked 39, or you could have picked 39.1, depending on how many decimal places you wanted to pick. So that's fine. Did you get a pretty similar number still? Yeah, okay. Yeah. So this this type of problem is a little easier because you're just dividing the moles. You just find the moles and divide by the liters. Unfortunately, that's actually the less important version, because that's like, when is that going to happen? When are you going to have a random amount of something and you dissolve it and then need to find the concentration? That's usually not happening. What's usually happening is something like 9.5, where you say, okay, I need this much of this solution, or somebody tells you, hey, I need this much of this, make it for me, and you have to go make it. So you have to figure out how much you're going to need to put in there to actually make it. So let's look at how we would do that. So we want 2 liters of a 6 molar NaOH solution. But we want to know how much how much actual grams of NaOH should we weigh out to make this solution. So to do that, we need to know how many moles we need overall. And this part we can kind of do like a conversion problem. So we can say, all right, we need 2 liters of a 6 molar solution. So a 6 molar solution means that we have 6 moles per each liter. So if we have 2 liters of a solution with 6 moles per each liter, because that's what molar means, that's what molarity means, 6 moles per each liter, except it's not Cl, it's OH, sorry. That means we need 12 total moles of NaOH. So you see how that's like a conversion? The liters cancel and we're left with moles. So that tells us how much NaOH we need in that particular solution. So then the last step is to convert that to grams, which we can measure. So we would go 12 grams. And then we want to get rid of grams. Whoops, not grams, sorry. 12 moles. We want to get rid of moles and instead have grams. And we add it up the same way. So 23, 16, and 1 is 40. All right, so 12 times 40 is 480. Is that right? I think? Yeah, okay. Thanks. 480 grams of sodium hydroxide. So this tells us now how to make the solution. We would, if somebody said, hey, I need 2 liters of a 6 molar sodium hydroxide solution, you'd say, okay, do the calculations. That means I need to weigh out 480 grams. I need to dilute that 480 grams out to 2 liters, and then I've got it.
So you just go backwards with this one, right?
Yeah, it's the opposite of what we did before. And in fact, when you're doing it this way, you can do it as just a whole line if you like it that way. So you can go liters times moles per liter times grams per mole, and that's it. Because then you're canceling liters, you're canceling moles, and then you're left with grams. All right. So since we just did that one, just to keep it in your head, why don't you try one of these other ones? Let's try C, because it's got one extra little step in there. Because now your volume is given milliliters instead of liters. So it's all the same, but you have to go from milliliters to liters first.
stuff, but if you follow just what we did before, you just take it.
All right, so this one's going to look the same. I'm going to do it in the line style, like where we do it all at once. Some people find that easier to follow along. The main difference here is you have to convert from milliliters to liters. You can actually use milliliters, but then you end up with millimoles instead of moles. So your final, if you did that all the way through, you could actually still get the right answer, but your final answer would be in milligrams instead of grams. So because the question here specifically asks for grams, we're going to convert from milliliters to liters and then go through that that way. So that's going to be 175 milliliters. And then we're going to go from milliliters to liters. Remember, we always cancel the unit we don't want on the bottom and then have the unit we do want on top. So we want liters. Then we want to cancel liters and go to moles of sodium nitrate. And then we want to cancel moles of sodium nitrate so that we get grams of sodium nitrate. All right, so now we fill in the numbers. 1,000 milliliters per liter. The concentration tells us the moles per liter. So that's 3 moles per liter. And then the grams per mole we get from the molar mass. So what was the molar mass of sodium nitrate? Oh, I heard it, but it was all a jumble. 53, 85, 85. Okay, go with 85. Yeah, that sounds right. Because you got to get 3 oxygens in there, the nitrogen, and then the sodium. Okay, so you put that all together, what do you get?
4.625 grams.
All right, so we'll say 44.6 grams of sodium nitrate. So you would take your 44.6 grams of sodium nitrate, put it in the volumetric flask, dilute it to 175 milliliters. You'd have your perfect 175 milliliters of a 3 molar solution ready to go for whatever terrible things you want to do with it. Okay, so those are the calculations you should be able to do, and we'll practice those in lab on Wednesday. We'll also do the homework because we'll have a quiz on Monday, and then that'll be in the exam on Wednesday. So make sure you're able to do those types of calculations. Take a look closely at the homework assignment for chapter, what are we in, 9? I always forget the numbers. For chapter 9 that's on Blackboard, because we are skipping some parts. So we're skipping some parts about the different concentration measurements, but we do want to make sure that you can do mass percent and molarity for the exam. Okay. We're also going to skip section 9.5, which is dilution of solutions, how to dilute solutions to get new concentrations from previous ones. You can look at it if you want. It's not that hard, but we're not doing it. So don't worry about that. All right, so let's get into some different types of solutions and how we name them. And we'll be doing this in lab, actually not Wednesday, but after the exam. So this is solutions versus colloids versus suspensions. All right, what do you think is the difference about these three? What does this speak to? Does anybody know? I mean, we just talked about solutions. Does anybody know what colloids or suspensions are? No. Has anybody ever had like medicine that was a suspension? What is that? Like what? What does that mean? Something you need to shake up. Yeah, exactly. Like that pink stuff when my kids have strep. Stuff's gross. You have to like shake it all up. So what's happening there? Why do you have to? What's different about it? What does it look different? It separates. Yeah, like if it sits in the fridge, something kind of falls to the bottom. So how is that different from a solution? Yeah, they don't separate. What do you think controls that? Why do some things separate and other things don't? Kind of. It's actually it is the mass of the particles, but it's because in a suspension you have larger particles. So we can kind of make this into a little graph and say that this has to do with particle size of the solute. When we did those examples of what suspensions look or what solutions look like at the molecular level, you saw like individual molecules or individual ions being surrounded by solvent. And the other side of that, a suspension, you'd have a big chunk. I mean, it doesn't look big to us, but down at that level, it's many molecules or ions all together. And they're still kind of solvated. They're still surrounded by the solvent, but they're too big to actually be held in solution. So they'll settle out over time. And then colloids are these weird kind of middle ground in between the two. So let's look at the properties of each and then look at some examples and kind of talk about which one's which and why. So rather than write this all out, we'll just take a table from the book which is on page 306. There it is. And we'll compare these three things. Right? So the solutions, what we've all just been talking about, individual ions, molecules that are surrounded by water. Particles do not settle. You can have a solution around forever, and the particles aren't going to go settle down to the bottom. And because they're involved with the solvent at the molecular level or the atomic level, they can't really be separated by these kind of physical means like filters or what we call semi-permeable membranes, which is just like a really, really fine filter, kind of like a cell wall. So the particles are so small that they can actually flow through anything that has a hole the size of a molecule, which is like almost nothing, which is so tiny. So the only way to separate those is through state changes, like evaporation. So you can evaporate the water in salt water and have salt left behind. Distill it, separate it that way. But there's no filter that you can pass salt water through and filter out the sodium. So that's a solution. On the other side, so we'll skip the middle one for now. On the other side, the suspension, we've got these particles that are so big, you may actually see them. If you let it sit, they'll settle right down to the bottom. And so you can filter that. If you take the filter paper, like a coffee filter or something like that, you pour it through, the particles stay on the filter, and the rest of it comes through. Now, depending on the type of particles and all that stuff that makes up the suspension, you could shake it up really well and have it actually sit and be like not settle for a little while. That could still happen. But if it ever settles, that's a suspension. And then the colloid is in the middle. So in the middle, you still kind of have, you're still at the molecular level, but really large molecules. So things like starches, proteins, those kinds of things can make colloids because they're so big. And what that means is the particles still don't settle. So they're still held in the solution. But you can separate them with these really, really special fine membranes called semi-permeable membranes that we'll look at, we'll use in lab in a couple weeks. Semi-permeable membranes are just a membrane, so what am I trying to say, like a barrier that has small enough holes that large molecules can get through, or that small molecules can get through, but not large molecules. The ones we're going to use is something called dialysis tubing, which is this, it kind of looks like plastic wrap, really, which is plastic wrap is also a semi-permeable membrane. And ions and things in solution can go through it, but large proteins, that sort of thing that forms a colloid can't go through it. Okay, so that's how those things work. There's a nice picture of that separation here. It's not a great figure because it's got a lot going on here, but let's take a look at it, and it kind of sums up all that stuff. So we define those three things often by how we separate them. So if we had a mixture of all three, you could find that if you let it sit, the suspended particles would settle, the others would not. If you filtered it, the suspended particles would come out, but the others would not. And if you put it inside a bag, like a plastic bag, the solution particles would make it through the bag and get to the other side, but the suspension and colloid particles would stay inside the bag. And that's all just a function of particle size. How big are those things? All right. Now that's really important in the body because we have all that stuff in there. In your blood, for instance, is all these different size particles, from cells, which are large, to proteins, which are in the middle, to ions and small molecules, which are the smallest ones in solution. So we think about how these things work with the membranes in your body, because your cell walls are also semi-permeable membranes. So these things will all also apply to that. And one of the factors that controls this is something called osmosis, or osmotic pressure. So what is this? You know? Biology folks? What's osmosis? Not quite. That's diffusion, but we'll talk about that also. Yeah, that's very related, so it's similar. Osmosis has this kind of very vague, broad use in everyday life, where it just means like things kind of magically going from one place to another. Like they say, like if you put your book on your head, you'll learn what's in the book through osmosis as it goes into your brain. That has nothing to do with what we talk about in chemistry. In the real definition, osmosis means water traveling through a semi-permeable membrane. So what happens is, I think this probably works best if we look at a picture. So we'll go to the book again so we don't have to draw terrible pictures. All right, so let me describe this thing for you. What you've got here is a container with water in it, and it's separated in the middle by this semi-permeable membrane. So this membrane that is only big, that has holes in it, but the holes really only pass individual small molecules. So what happens is if you put pure water in one side, and you put water with a solute, so a solution in the other side, the energetics of how the solutes and solvents interact mean that the pure water will flow toward the other side to try to equalize the concentration. So you've got a lot of concentration here, you've got low concentration over here, so this water is going to go try to make that concentration lower. And so it will, through osmosis, go through that semi-permeable membrane. And the reason that's called an osmotic pressure is because look what happens to the liquid levels. Over time, this side is going to have more water in it. So this water has pushed this up. And because of atmospheric pressure, that's actually creating a pressure. In order to raise a liquid level like that, that means that there's a pressure going on, that water is pushing upward on the atmosphere to fill that thing up. So that's why it's called osmotic pressure. So there is a positive pressure on that membrane going from left to right as the water pushes and diffuses through. And that's what osmosis is. Osmosis is water going through this membrane to try to equalize the concentration. So the reason that this is important for us is because this is what happens with our cells, especially our blood cells. Well, we'll just leave that up there. We'll do our definitions over on this side. We can define an isotonic solution as a solution with the same osmotic pressure as what we call the intracellular fluid. So an isotonic solution in your body doesn't mess with your cells, because if you imagine the cell membranes as the semi-permeable membranes, an isotonic solution has the same osmotic pressure as the liquid inside the cell, which means no water is going to be pushing in or out. There's no osmotic pressure when you have an isotonic solution. But what could happen if that's changed? So what happens if you put cells in pure water? Pure water would have a higher or a lower concentration of solute than inside the cell. What has more solutes? The fluid inside the cell or pure water? It's got to be inside the cells because we know it has something in there. So if you put pure water, which direction is the osmotic pressure? Is it pushing into the cell or is it pushing out of the cell? Well, it's always going both, but which direction, like overall, is favored? In, out? Why out?
Because it must equalize.
It wants to equalize.
It wants to pull from the cells
Pull what?
Solute.
Yes, you're correct. But
Mass.
with osmosis, we're talking about the movement of the water, not the solute.
The water wants to go in.
So the water wants to go in. Is that what you're going to say?
Yeah, just looking at the example of
Yeah.
the side with the solutes wants to hold the water in.
Right. So if you imagine that as so the pure water on one side, you imagine the other side is inside the cell, the water is getting pushed inside the cell. So what's going to happen to that cell eventually? It's going to burst. It's going to rupture. Yeah. And so that can be a problem or a good thing. We'll depending on what you want to do. But if in that situation, you have what's called a hypotonic solution. So hypotonic means lower solute concentration. So this will push water into the cell via osmosis. So that's called a hypotonic solution, and eventually that will push so much water into the cell that the cells can burst. One of the toughest things about this is keeping the direction of everything straight. So we're talking about the movement of water. A hypotonic solution has a lower solute concentration, but it creates a higher pressure. So a hypotonic solution has a higher osmotic pressure than an isotonic solution. Because it's pushing water into the cell. So a lower ion concentration, and we're used to that term hypo meaning lower, so it's a lower ion concentration, but that's causing the water to push into the cell, so it's causing an increase, a higher osmotic pressure. And then the opposite of that is hypertonic, which is a solution with the higher solute concentration. And this will pull water out of the cell, because now the solute, now it's sort of like the opposite. It's like the cell is on the left and the outside is on the right. And so the water is being pulled out of the cell to try to equalize the concentration. And so we would call that a lower or a negative osmotic pressure. The pressure is on the opposite side of the membrane because the water is pushing outward. And what happens then is that can also destroy your blood cells by just desiccating them. Yeah, and they all kind of just. Yeah. There's a picture of that in the book also. So here you've got those three types of solutions from left to right. The normal isotonic solution. The hemolysis is the name for the red blood cells bursting from getting too much water in them. And then prenation is the term for the water coming out of the cells and then getting kind of shriveled up from the opposite direction. All right. Now we should say here, we didn't talk about the specifics of the way that we describe the concentration through something called equivalence. We're skipping that part. But this has to do with the number of particles. So when we talk about the concentrations, being equalized, what we really care about is the number of particles. So that's, again, molarity. So molarity becomes important because that's a count. So when we have what we call a normal solution, whether it's a saline solution or a glucose solution that's going into your bloodstream, it's the molarity of those solutes that's important. Just as an example, go back up here. So some examples of isotonic solution. Isotonic solution is about 0.3 molar in whatever kind of solute you want. So any kind of solute you want, if it's about 0.3 molar, that's going to be isotonic with the intracellular fluid. But if you use different types of concentration measures, that could be different for different amounts. So for instance, a 0.9% sodium chloride is what we call normal saline. That's mass by volume. So 0.9% mass per grams per milliliters is normal. But 5% glucose is also isotonic. Very different numbers, 0.9% versus 5%, and that's because of the different molar masses and all of that. But those are both, if you do the conversions, and we'll do that in lab in a couple weeks, we'll do it together. If we convert those units from grams per milliliter to moles per liter, you find that actually both of them are 0.3 molar in total dissolved particles. So by counting those particles, that's how we can define an isotonic solution. All right. And the last thing we're going to talk about, which again we're going to do in lab in a couple weeks, is called dialysis. And this is happening at the same time as the osmosis. Osmosis refers to the movement of water, and dialysis is the movement of solutes. So this is a picture from the book. This is what we're going to do in a couple weeks. You put some stuff in a semi-permeable membrane. In this case, the little yellow spheres are solution particles, so sodium, chloride, glucose, things that are dissolved. And the big red ones are colloidal ones, proteins, starches, big molecules. Over time, those little molecules can also diffuse through the membrane just like water could. So not only is water moving back and forth, but the solute particles are as well. And this is known, and when it's a solvent particle or a solute particles moving, we call that dialysis. So this is what your kidneys do. This is how we filter out all those impurities, salts, and things in your blood, is by having regions that are less concentrated in across the membrane so that they come out. If you need to go, if your kidneys aren't working properly, and you need to go have dialysis, like externally, you go to a machine, they pump your blood through a thing, and it's the same thing. So the solution, the dialysis solution, is going to be deficient in the things that you want to come out, and then it's going to bring those things out as they pass through the membrane. And so that goes both ways. All right, questions about those definitions? So one of the things we want to be able to do is to think about what direction things are going to go and how they're going to flow. So for instance, we've got two compartments separated by a semi-permeable membrane, A and B. So we want to know, for each of the following, they're separated by a semi-permeable membrane, which side is going to increase in volume? And I mean, it's always kind of the same thing. So all of these, we'll just look at one of them, but let's look at A, for instance. So you've got 5% sucrose on side A, You got 10% sucrose inside B. So because there's a difference in concentration, there's going to be movement of water. There's going to be an osmotic pressure. So which side will end up higher?
B.
Go to B. Anybody A? Anybody A? No. Anybody else B? Well, not anybody. Be even? Okay. So why B? Somebody said B.
That has more solutes.
Yeah, so greater solute concentration on side B. So that means that the water is going to go toward side B to try to equalize the concentration. So the water always moves from the lower solute concentration to the higher solute concentration, and therefore it'll push that level of B up. Anytime you have a difference in concentration, the water is going to move across that membrane to try to equalize it.
So will it be equal or will B have more?
B will end up with more, because the water will push across the membrane from A to B, which pushes that B up more. In that situation, B is, it's this situation. Instead of pure water, you can think of this as like a lower concentration versus the higher concentration. And the water will always flow over to the side with the higher concentration. So that's one way we can think about those. All right. We have a little time left. So another way we can ask this, grab these pictures. All right, so we got another semi-permeable membrane. I'll jump right back to it, but I have to grab this table also. All right, so same idea. We've got this membrane separating A and B. And then in each case, we've got a different solution, or the same in some of them. So the question is, if we start with them at the same level, which of those three is it going to look like after time? So for the first one, if we put 2% starch in A and 8% starch in B, what's it going to look like over time? 1, 2, or 3? 2, right. It's going to flow from the lower, the water flows from the lower concentration to the higher concentration. What about B? If we put 1% starch in each, what's it going to look like over time? 1? Yeah, not going to change because there's no difference in concentration. What about C? If we put 5% sucrose in one and 1% sucrose in the other, what happens? Go with 3? Yeah. Yeah, that's actually a little tricky with sucrose, I think. It's not a great question in that way because sucrose will also diffuse through the semi-permeable membrane. So it's slower, but over time, if you live enough time, you would imagine that everything will end up equalizing because the sucrose will be able to go through the membrane also. So initially, yeah, the water will push and you'll have an osmotic pressure and you'll end up with 3. But over time, it could perhaps equal, I guess not, because it'll end up with the same concentration. So 3 is probably the best answer there. And then what about D?
Probably look the most
Like 1? Why?
because there's such a little amount that you eat in both sides, 1%.
I mean, that's true, but that's a big difference relative to each other. One's got 10 times the concentration of the other, right? Like I might argue that that's a bigger difference than A, even though, well, maybe not.
Relative to each other, yeah. But
Relative to each other, yeah.
compared to the amount of water
That's true, but relative to each other is what's important here, right? Because that's what's controlling that water movement. So I think it's still safe to say that that number 2 is the right comparison for those two. All right, so that's solutions. Make sure you take a look at the objectives for this chapter so you know what you need to do and practice in the homework, especially with those concentration calculations. So you want to be able to understand what solutions look like at the molecular level, how we calculate the different measures of solution concentration, and how to use that, like to create solutions, to use solutions, and then the stuff we just talked about, different particle sizes, and what the effect of those things are. Yeah?
Is there any other portion of skipping besides 95?
Let me check. So you can look at it's listed on Blackboard in the objectives and everything. We're skipping parts of some of the other sections, like the thing about equivalence in 9.2, the stuff about volume percent and mass by volume in the next one. So there's like a few portions, but not a whole section. But if you stick to the objectives and the reading assignments, it should say on there. All right, so stick around. We've got about 15 more minutes if you have questions or anything. Otherwise, I'll see you for lab on Wednesday.
Do we have to know the Boyle's law, Carl's law, the Lucy's law?
Yes, but you don't have to know them by name. So you have well, just like what we did in the quiz today. So like understand what they are, like what the relationships are, but you don't have to know them by name.
Okay, so understand what they do.
Right. Yep, thanks.